So welcome to the end of the semester. That's my standard line this week. So we want to find this, which is slightly different than the flux integral, because instead of f dot mds, it's the curl of f. Now, the curl of f might be more complicated, it might be less complicated, but it does involve partial derivatives. So there's a tendency that things are a little bit smaller. Okay, so f is z squared, x squared, y squared. And s is, let's see, 4x plus 2y plus z equals 12. It's that part in the first octant. So we know what that looks like at this point. You know, in this class, we tend to use familiar shapes. So if I want to know what this looks like, about 3 units in this direction, about 6 units here, about 12 units here. All right, so it's something like that. Okay, go ahead and mute yourself if you're not here. A lot of background. So this is our surface. Now the surface is flat, which definitely makes it easier because then the projection is just going to be that triangular region in the XY plane. So when I'm looking at the triangular region in the XY plane, let's go ahead and identify this right away because we can. So in the XY plane, that means z is 0. So that would be 4x plus 2y equals 12. So when I'm trying to work this problem, whether I want to do dx or dy, depends on what's going to be an easier integration, what's going to be an easier setup. So we'll get to that in a moment. So now in this case here, excuse me, what I want to start by doing is figuring out exactly what my normal vector looks like. So I need a gradient vector. In order to have a gradient vector, there's two things I need. I need the ds. So that means I have to solve for z. So let's call our f of x y, which is z. That's going to be 12 minus 4x minus 2y. I need that for the ds part, but then I also need a gradient vector for the n part. And we know that there's a lot of similarities. Excuse me. So let me go ahead. No, I'll put it up here. So my fx is -4. My fy is -2. So I'll do my ds right here. So then the ds is going to be the square of -4 plus the square of -2 plus 1 under the root dA. So that's what 17 plus 4 plus 1, or root 21 dA. Now, hopefully, if I do this right, I'm going to see the root 21 show up in my gradient vector somehow or another. So now let's do the gradient vector. So for that one, I need to have a g of x, y, z. Now, do I go z minus function? Do I go function minus z? In other words, when I'm looking at this, do I want the z on this side with a negative coefficient, or do I want everything on this side so the z has a positive coefficient? Now, I just drew a picture of the surface a moment ago. Do I want to have a plus z or a minus z? That's what it comes down to. Anybody want to try that one?
Z minus function, we want to have a plus z.
I want to have a plus z because I don't know if you can see, my angle was outwards, right? So that if you thought about again, my real quick drawing here, right? My normal vectors are going to point above the xy plane. They're not going to point down towards the xy plane. So I want the z to have a positive coefficient. So that makes it really easy. Just look at this. Just subtract 12 from both sides. It's sitting right there in front of me. So there's my gradient vector. Or excuse me, there's my g function, and that's where I'm going to get my gradient vector. So that would be 4, 2, 1. The length of my gradient vector, 4 squared, 2 squared, 1 squared, that's my root 21. Hey, good. That's a very good thing. So now I can say then my normal vector is 1 over root 21 times this. Now, I can distribute, but I'm going to be canceling it with this later anyway, so I might as well do this. There's no skipping finding the normal vector. And you say, well, but I'm doing double duty. Well, no, not exactly. Because remember, depending on which way we subtracted, these could all have negative coefficients, and that would absolutely affect the final answer. So you actually need to go through these parts separately, because the only part that's the same is this. Okay, that's going to be the same, but the vector itself I still need to find, because I got to be able to do the dot product. Okay, so finally, I'm going to have to race in a minute, but not yet. Finally, I need to do the, we need to do the curl of F. I haven't done the curl yet. So the way I like to do the curl is I'm really lazy. I just go like this. Partial with respect to X, partial with respect to Y, partial with respect to Z. My ducks in a row here. So my curl of F is, excuse me, boom. So what's that? 2y minus 0. 2z minus 0. 2x minus 0. So obviously just 2y, 2z, 2x, and all of them positive. Again, if I make a mistake and I get a wrong sign, that will definitely affect my final answer. So now the last piece of the puzzle before I write my integrals, I need to figure out my integrand, which will be curl of F dotted with n ds. So let's write that down. So first thing is I'm going to do the curl dotted with this part. And so what's that going to be? Looks like 8y plus 4z plus 2x times 1 over root 21 times root 21 dA. See how nice that is? That's so clean. Now, this is going to show up in a double integral. So what do I need to do now? Because I can't put this in my double integral. Not exactly. Anybody, any suggestions? My double integral can only have 2 variables. This has 3. So anybody have an idea?
You just sub in the z.
Yeah, let's sub in exactly that. So we will replace z with 12 minus 4x minus 2y.
This is the quiz we just took, right?
Yeah.
Oh.
Hopefully this is what you guys did, but
No.
I'm showing you step by step why we're doing each thing when we do each thing. So when I clean this mess up right here, excuse me, I believe that's going to be 48. Looks like a negative 4x plus 2x, excuse me, negative 16x plus 2x, so negative 14x. And negative 8y. Okay, go ahead and mute yourself. Josue, I think that's yours. And then the y's cancel. So I think that's it. This reduced all the way down to this little quantity right here, dA. So now let's go ahead and answer the question. I have water somewhere. I just don't know where it is. I need to drink some soon. Oof. So now this is going to equal the double integral over the region in the xy plane of 48 minus 14x dA. Oh, that is so clean. So now we have to decide, do we want to do dy dx or do we want to do dx dy?
It would be better if you do dy dx.
How come?
Because when you solve for y, you get 6 minus 2x.
Okay, so there's 2 ways I can look at this. So we said it's this. So if I solve for y, I will get what, 6 minus 2x. If I solve for x, I'll get 3 minus 1/2 y. So right off the bat, you're saying, I think I want to solve for y because I can avoid the fraction. That's not bad. It wouldn't be that terrible, but there's actually a better reason to choose this one.
It's we don't bring an x squared in the
Exactly.
first.
This is the ultimate lassitude. That's a word. I coin it all the time. You see, when I integrate this with respect to y, everything's first power. And then I would substitute the y limits. If I integrate this with respect to x first, I'm going to have an x squared, and then I'm going to throw something in, but then I got to square it. Not that that's evil, but that's just more algebra than multiplying by a constant. So in this case here, there's two reasons to choose this. One is there was no fraction, but even if there was a fraction, it's because this doesn't have a y. I'd rather integrate with respect to y first, because then I got no variables to powers. See, so that's kind of a good way to make the choice, is which one's going to make it easier on me. So we decide we're going to go dy dx. So what does this look like? Well, this looks like a triangle. That's y equals 6 minus 2x. So that would be 3 comma 0. That would be 0 comma 6. But we said we're going to go this way. So the range of values of y is y equals 0 to y equals, sorry, to y equals 6 minus x.
0 to 3.
6 minus 2x. And then x is going to go from 0 to 3. Now, from this point on, oh my goodness, this has to be trivial. I mean, this just can't kick our butts. One of the things that makes me sad is that you get to here, and then we get a wrong answer because we make an arithmetic error. If you got this for you, got to get the right answer because you did all the heavy lifting already. So 48y minus 14xy from 0 to 6 minus 2x dx. So I've got 48 times 6 minus 2x minus 14x times 6 minus 2x.
It would be the same thing if you just put 48 minus 14x times, kind of like a...
Yes.
Yeah.
If I had, excuse me. Hang on. Oh, hold on. Here it is. Okay, sorry guys. I don't want to keep clearing my throat as I'm choking to death. You guys can't really do CPR, through the computer, I don't think. So Josue suggests if I factor it here, 48 minus 14x, and I do that all times y. Let's do that. That might make it a little bit cleaner, right?
Yeah.
I don't want to say cleaner, a little bit shorter. How's that? I like that idea because, again, laziness is important. Laziness means you're looking for shorter ways, not creating more work for yourself. So 6 times 48, so 288. Negative 96, negative 84, so that'd be negative 180. And then plus 28x squared. I think that looks right. Does that look okay to everyone?
Yes, sir.
Something that ish. Okay, so now let's finish. So that'd be 288x minus 90x squared plus 28 thirds x cubed from 0 to 3. And if I get out my handy dandy calculator, right, they're going to cancel. I'm sorry.
I'm looking at my work, so it's like 252 minus 810 plus 864 equals 306.
306. I think that's the correct answer. Now, the problem is not to get to here. The problem is to get to here, as you all realize, because if I can get to here, that's a piece of cake. But what if I get to here and it's beyond fathom? It's just too difficult. That is actually possible. And that question usually will be set up the integral, right? That was last quiz, because I gave you a question that to integrate would have been extremely difficult. Possible, but very difficult. So in this case here, getting to here was the whole key to the problem. So getting this, the region itself really didn't have a lot to do with it as much as for the limits, because it's very simple that this, or not simple, it's very possible this could have been, a polar conversion kind of thing. So now let's do the next problem. It's the same thing. I want to find this quantity. I like these kind of problems. I don't want to say it's a game, but it's a kind of situation where if I start correctly, they tend to kind of self-navigate. I mean, I just write the next thing that it has to be. So in this case here, my f is zxy. Do you notice that it's kind of odd that in both problems I have x, y's, and z's, but kind of out of order? Do you know why we have them out of order?
So the cross product
Because
cancels.
of the curl. See, when I do partial with respect to x, partial with respect to y, then partial with respect to z, oh, I'm going to do a y, I'm going to do a z, I'm going to do an x. You see, when I do those, if I had this in the form x, y, z, then the curls would probably all be zero vectors. And that's boring. We don't want the curl to be a zero vector. Yuck. There's nothing to do. So in this case here, let's see, my surface was z equals 36 minus x squared minus y squared, which of course, one of our personal favorites, right? Let me use a different color here. Right? I know it's terrible, but our downwards opening paraboloid that intersects on the xy plane. Yeah, because I said z equals 0 is the other boundary. So it's the paraboloid and it stops on the xy plane, which means my region in the xy plane will be that circle, which definitely is nice. That'll make life simpler, but it also means that I suspect that I'm going to go to polar coordinates. So let's start with, let's see. Well, clearly, the way this is described, I can already call this my f of xy. All right, so when we do fx, that's negative 2x. Fy is negative 2y. So my ds is or 4x squared plus 4y squared plus 1 dA. And that's clean. Now I need to do my gradient. So which way are these normals pointing? Are they pointing below the xy plane or above the xy plane?
Above.
Yeah, in fact, if it makes it easy, just go to the top. Oh, that's pointing straight up. So my normals are all pointing in a general that way direction, which simply means that when I create my g function, I want it to be plus z, not minus z. That's it. And I tried to illustrate this over the last several weeks because this problem comes up, but it's actually that easy. That's why we don't say there's an automatic form that you're always going to do when you do your g. People say it's always f of xy minus z. Well, no, half the time it's that. The other half of the time it's z minus f of xy because it depends which way this guy points. So I'm going to let g of xy z, okay, I want the z positive, so I'm going to throw everything on that side. So positive x squared plus y squared plus z minus 36. Okay, does it matter? Yes, because when I take the gradient here, if I subtract it the other way, my gradient would be the opposite sign, which means the final answer to the problem would be the opposite sign. And that actually is quite important. Okay, so my gradient vector is 2x, 2y, 1. The length of my gradient vector should look like that exactly. 4x squared plus 4y squared plus 1 under the root. And therefore, my normal vector is 1 over the root 2x, 2y, 1. All right, so the last piece of the puzzle that I need before I can start setting up my integration is to find the curl vector. Oh, I can do this right now. I got that all ready to go up here. All right, so 1 minus 0, 1 minus 0, 1 minus 0. Are you kidding me? Curl vector is just 1, 1, 1. Yep, curl vector is just 1, 1, 1. That makes my life a little bit easier. So now, let's see. I've got my normal vector here. I've got my ds here. I'm kind of cordoned off this section here. So now let's do our curl of f dotted with n ds. Okay, so I'm going to do this dotted with this, and then that quantity gets multiplied by this. So those guys will end up canceling. That's why we get everything right here. Then we can say this is going to be what? 2x plus 2y plus 1 dA. Oh, that is nice. And you know what else is really nice about that? There's no z. There's no z in there, so I don't have to substitute anything in. I can integrate this directly. Awesome. Okay, so let's now, hold on. Last thing is, I don't think we stated this. What is our region in the XY plane? Let's do that still. The region in the XY plane means z is 0. So that means it's x squared plus y squared equals 36. So the region in the XY plane is that circle of radius 6 centered at the origin. So, I mean, obviously, we're going to go polar here. So let me go ahead and I think I can erase this stuff now. So this will become and I think we all agree we're definitely going to go polar, not cylindrical, polar. It's only a double integral. So we said a circle of radius 6 centered at the origin. So 2r cos theta plus 2r sine theta plus 1 r dr d theta. Okay. So I need to distribute. So 2r squared. In fact, if you want, you can factor out these 2r. So you can say 2r squared times cos theta plus sine theta if you'd like. Nothing wrong with that. But don't forget that r plus r dr d theta. Okay, so far so good. So when I integrate that, I will have 2/3 r cubed cos theta.
Professor,
Yes.
would it be the same thing? You just leave the r's distributed like that. You know, just distribute the
Oh,
r outside, and you get 2r squared cosine theta plus
Yeah.
2r squared sine theta plus r.
absolutely. I'm just taking your lead. So you.
Right. No, I know. I'm just asking because I have it. I just went the hard way this time.
Oh, I wouldn't say it's the hard way.
More work.
There's a tendency when you got the signs and things get lost.
Yeah.
We all know that way, and that's the worst thing that could possibly happen is that we lose something. No, it won't matter because in the next step, it's all going to be cleaned up anyway. So here, all right, so what have I got? So r cubed, so that'd be 216 times 2/3, that's 144. And again, whether you distribute or whether you don't distribute, it doesn't make any difference. It's going to be 144 of these and 144 of these. And then what, plus 18?
Yes, sir.
Something like that. Now from there, this is kind of nice because I'm integrating sines and cosines, and then I'm throwing in a theta here. So I think we're just about done. So I'm going to have 144 sine theta minus 144 cos theta plus 18 thetas from 0 to 2 pi. Now, why do I love 0 to 2 pi?
Because the sines and cosines cancel.
They're gone. They're both 0. This is 0 at both ends. This is 1 at both ends, but they will cancel. So all I'm left with is that guy. All right, crowd goes wild, confetti everywhere. One of the things we really like because of the 0 to 2 pi, so unless that angle is a double angle or a half angle or something weird, usually when I do this 0 to 2 pi, usually all the sines and cosine stuff's going to go away. Now, not necessarily true for other functions, but certainly the sine and cosine. So that's it. Now that's a perfect example of how Stokes' theorem works. And in terms of the actual algebra you're performing, it looks very much like the flux. It's not the same thing because we're finding the curl of f, but I'm taking the curl of f and then I'm dotting with n, I'm doing the ds just like we do with the flux. So the format feels very much the same. Okay, now I'm going to do the same thing on Tuesday. I'm going to go in a little bit of detail just so that there's no ambiguity. See, it's one thing to get the right answer, but do you know what you said, or did you just, you found an example in the textbook, or you found an example that I put on the notes, and you just said, let me follow the example because the numbers aren't that different, and you got a perfect answer. But if you did, do you have any idea what you just said? And that's the most important part, because what if you're asked to do a question that doesn't look the same? Right? You want to know that from beginning to end, you've got this. And the way we did this is like we did the other problems. We found our gradient so we could find our normal. We found the DS. We then did the dot product. In this case, we dotted it with the curl. Before, we dotted it with the given F. So the structure, the format, the order of steps, pretty similar. Now, the exam is a week from today. Hopefully you've started looking at things already. And if you haven't, we're running out of time. So is there a priority? Is there a sort of an order of things you should do? Yes. I always suggest when you're preparing for an exam, retake your quizzes. It's good practice. You got a key, you can go through and make sure that if you got it right, you still know it and so on. When you're taking a final exam, I always suggest retake your exams. You have 3 exams and 3 practice tests. Yes, you have a lot of quizzes, but the quizzes might take you a lot longer to get through all of them. So I always suggest starting with the exams, retake the exams. This is why I give a detailed answer key. I don't do that because it's convenient for me. I do that so that you can retake a test, grade yourself in one of 2 things. If you got it right the first time, do you still remember how to do it? That's the most important. And if you missed it the first time, have you figured it out? Because that's how you can improve your grade, that second situation. And as you're going through, you kind of go through every possible question we've seen. If we didn't do it on an exam or a quiz, it's not going to show up on the final. In fact, the final is big ticket items only. Your exams were all over 7 or 8 lectures. The final is over 26 lectures. So on an exam, I could ask you the same question more than once. I could do multiple things, different versions of the same kind of stuff. But on the final, things actually have to be left off because you only have 2 hours. See, if I wanted to ask you every single question, it'd be an 8-hour test. So I have to sample from all the things in the course. So the suggestion I give every class is similar in that if you could go to all 26 lectures and say, what was the single most important thing we did this class? If we could prioritize all the problems, all the types, if we could say, what's the most important problem we did, then that's the problem that's going to show up on the final exam. But that would still be 26 problems. The final is not that long. The final is exactly 14 questions, and you're going to do 10 of them. It's very similar to the last exam. Now, the 10 questions will all be equally weighted. So therefore, if you aren't sure of one, or if you go, no, that one's going to take me a little longer, put it off. Okay. And as always, it is encouraged to do an extra problem. You don't have to do an extra, but it's always a good idea if you have the time to do one as insurance, because I don't know which one's your extra problem. If you turned in 10 great problems, you don't need insurance. But if you turned in 10 problems and you're not sure of a few of them, to do an 11th would probably be a good idea, but that means you got to work fast enough to give yourself time to do the 11th problem. Okay, so as you're going through the problems and you're knocking things off, the most important thing is to go over the problems that you've gotten right in the past, because the things you have to get right on the final are problems you've answered correctly before. Okay, problems that you've never gotten, you may not get. But then again, I might not ask that question, or I might ask that question and you choose to skip that question. Now, the one thing that I hear so commonly from students, and I have given over 10,000 final exams, I hear the same thing. A student will say, I studied this many hours, fill in the blank with some unreasonable number of, millions of hours, and I still bombed my final. Well, I already know why they bombed their final. They just told me they studied for their final. So what, isn't that what we're supposed to do? Absolutely not. Studying means you're still trying to what? Anybody? What do you
figure it out?
Trying to learn it. You can't study for a final. You review for a final. That's it. So when you're going through there and reviewing, there are things that you have not gotten this semester, and there are things you're just not going to get this semester. And you know what? As long as that list isn't very long, it isn't going to matter. I'm not going to ask you only questions you don't know how to do. I'm going to ask questions that are generic and represent the whole course. Most of them you will know how to do because you've done them before. What you've got to do is go back and make sure you can still do them. If you got 100% on exam 1 and you haven't looked at it, that's a bad idea. But if you got 100% on this last exam, do you really think you're going to forget it in a few days? No. If you did well on exam 3, you probably don't need to review much at all because it's still going to be fresh. And the fact that it involves integration means you're already got your integration skills. You were doing partial derivatives and cross products on this last exam. So those are things you may not even have to review much at all. Now, what I will not ask you on the final are detailed questions, really, really specific things. For example, we did things involving, maybe continuity, or we did things, oh boy, I'm just trying to, identify the surface or things like that. That's part of a bigger picture. When I'm doing an integration and I'm trying to set up a volume, I need to know what a surface looks like. I'm not going to say, what is this? Oh, it's an elliptical hyperbola. That's a final exam question. No, actually, that's a high school algebra question. That's not a calculus question. To identify something as a parabola is not really something that you learned in Calc 3. That's something you already knew. You're identifying things in 3D so you could answer surface areas and volumes. So the problems that you're going to do, again, they're big ticket items. They're the bigger exam problems. The Lagrange multiplier problem, or the normal and tangential component of acceleration problem, because that involved a little bit of work. That's why you're only going to do 10 on the final exam, just 10. And so if you go look at the last exam, most of the problems were not very long. If you look at the key, a lot of the problems you'll say, there just wasn't that much writing, but I only had to do a handful of problems. And the reason is they were all challenging enough. Well, several of those are going to make it to the final. We had 3 lectures that did not show up on any exam. Clearly, that's fair game for the final. Now, all 3 won't make it to the final. If I'm asking you 14 questions over 26 lectures, it doesn't make sense if 3 of the 14 are the last 3 lectures. But it does make sense that a couple of them certainly could come from. Okay. And so, everything is fair game. And so as you're going through things, just making sure. So that's what I want to make sure everybody understands. Now, formulas. The question I keep getting is, should I use or can I reuse my formula cards? Yes, but don't. No. You may use an 8.5 by 11 sheet of paper, one side only. I would start over. The whole point of the formulas is to reinforce theorems and definitions and formulas in general. If you simply use a card you made for exam 1 and haven't looked at it since, that's not going to be very useful. Plus, there's information you put on there that you may not need to. There's information you forgot to put on that you probably need to. So I would prefer that you start from scratch, make a new one. And this is where you go through, identify every important theorem or definition or formula that you think is relevant, put it down in an organized way. Then when you sit down and take the test, you're probably never going to look at it because you've reinforced it over and over again. You can't put down the calculus formulas like antiderivatives and things like that. You're supposed to know that. But let's face it, aren't most of the problems sines, cosines, e's, polynomials? In other words, they're the less challenging things is what we've been doing all semester anyway. Your ability to do partial derivatives obviously is critical, but that means you have to know your Calc 1 derivative formulas. But again, we haven't been dwelling on the obscure. So you're not going to see any inverse hyperbolic cosecants, things like that. But you ought to be able to differentiate a tangent function or, the little things. I would suggest strongly that you start the formulas sooner than later, because what will happen is you start it and then maybe every day you'll think of something and then you'll add to it. A lot of you are going to make the mistake of waiting till the very last minute and then you're going to put it together knowing that you're going to leave off some important information. The other thing that I always recommend is that you compare. So Josue, when you have your perfect card, and compare it with Ian, you guys exchange however you can do that and say, oh, wow, you have one that I forgot, is usually the response. And that way you can make sure that you don't leave off anything that you deem important or you deem relevant. Okay. The exam is during exam time. I haven't had anybody ask me otherwise, but I always make this available. I know a lot of you have all of your finals literally in a row. I give a discrete math test on Wednesday morning, and I had 2 students tell me they walk out of their discrete math test. They have 5 minutes, I figuratively speaking, walk out. They have 5 minutes after the discrete math test to take their physics test. And then they have 5 minutes after their physics test to take their OChem test. And then one other one said that, and then I have like, a half an hour, and then I take my like engineering 240 or something ridiculous. That's just wrong, but that's literally what people are looking at. So if you have a situation where you have multiple tests, particularly in a row on Thursday, yeah, you can take mine a day early. I give 2 finals on Wednesday. It's not even a big deal. Every exam in every class I've given this semester, I've had at least one person take the exam outside of class because it was convenient. I've had somebody take the exam, maybe a couple days early because of other things. I have some military folks that were in situations where they said, you know what, I'm on duty that test. Can I take my test a day or 2 early? Yeah, we just got to figure out the logistics. Yours is the last final I give. I give one Thursday morning and I give 2 on Wednesday. If your life is made easier by you taking your final on Wednesday, no big deal. I'll just have you take it with one of my other classes. It's actually not even inconvenient. Okay. But you need to make arrangements way ahead of time, because whenever you want to take an exam outside of class, it's the logistics that we have to address. I'm not going to give an exam, in the evening on Wednesday. I'm going to be grading finals in the evening on Wednesday. Plus I've got other things. So if you want to take it outside of class, it has to be with another class while I'm giving a final, because then you can I just give you that link. And you just go to that Zoom link and take the test like everybody else, camera on you. No, it's not even a big deal. Okay. So at this point, I'm going to stop recording.